Welcome back. In this lecture, we'll explore an important new tool, the one-shot instruction, often called a transitional contact. This instruction allows a PLC to react to a momentary change in a signal, even if that signal stays on for some time. We'll also take a look at down counters and see how they work alongside up counters to track items entering and leaving a process. By the end of this session, you'll understand how to use one-shots and counters confidently in real automation programs. A one-shot, or transitional contact, is used when we want the PLC to react only once when an input changes state, even if that input stays on. The one-shot can be triggered by a momentary pulse or by a signal that comes on and stays on for a period of time. No matter how long the signal lasts, the one-shot remains true for just one PLC scan. Then it resets itself. It stays off until the trigger goes off and comes back on again. This makes one-shots essential for preventing multiple triggers or unwanted counts. There are two basic types of transitional contacts. The first is the off-to-on transitional contact, which produces a pulse when the input signal rises from false to true. This is known as a rising edge. The second type is the on-to-off contact, which pulses when the signal falls from true to false, a falling edge. In both cases, the one-shot lasts for one PLC scan only, ensuring that the logic detects each event once, and only once. Allen Bradley SLC 500 controllers use the one-shot rising, or OSR, instruction. It's an input instruction that lets an event occur just one time, even if the input condition stays true. In this example, the limit switch labeled LS1 turns on, and the OSR instruction sends a one-scan pulse to reset the counter. This guarantees that only one reset occurs per activation, no matter how long the switch remains closed. The OSR is one of the most useful instructions in industrial control, especially when combined with counters. Here's how the OSR is applied in a typical up-counter program. Each time a proximity switch detects an item passing on the conveyor, the one-shot sends a single pulse to the counter input. Without the one-shot, the counter might add multiple counts if the sensor signal bounces or stays true too long. With it, the counter increments cleanly by one for each distinct item, ensuring accurate totals. In this example, the system counts boxes moving down a conveyor line. The counter has a preset of 50, meaning that when 50 boxes are detected, the done bit energizes and stops the conveyor motor automatically. This allows operators to fill a truck or package batch precisely, and then reset the system for the next run. The preset value can be changed as needed for different product lines or lot sizes. Let's walk through the operation. The start button energizes the conveyor motor. Each passing box is detected by the proximity switch. The OSR instruction generates one pulse per box, incrementing the counter. When the total reaches the preset, the done bit turns on and stops the motor. This logic prevents multiple count from a single box and provides a clean, automated stop once the required total is reached. The OSR pulse remains true for only one PLC scan and then resets, even if the input stays on. This ensures each box is counted once. After the counter reaches 50, the done bit changes state, stopping the motor and resetting the accumulated value to 0, ready for the next batch. This automatic cycle is both reliable and efficient for repetitive production operations. Operators can also stop or restart the conveyor manually at any time. The counter's accumulated value is retained, so restarting the system continues from where it left off. When needed, pressing the reset push button clears the count and resets the process back to 0. This flexibility makes the system both automated and operator-friendly. Let's now look at a live simulation of the up counter in operation. On the left side of the screen, we see the process simulation window, showing a conveyor, a proximity sensor, and a solenoid control valve. On the right, we have the ladder logic diagram, where the up counter and the OSR instruction are programmed. When the operator presses the start push button, the conveyor motor labeled M1 energizes, moving boxes beneath the proximity sensor. Each time a box passes the sensor, the input signal, I1/3, briefly turns on. That signal passes through the one-shot rising instruction, which generates a clean, single-scan pulse to the count-up instruction. Without the OSR, the proximity sensor might stay true for several scans as a box moves past, causing multiple unwanted counts. But the one-shot prevents this by allowing the counter to increment only once for each distinct detection. You can actually watch this happen in the simulation. The ACC, or accumulated value, increases by 1 each time a box passes, while the input flashes momentarily. The preset value in this simulation is set to 50, meaning the conveyor will stop automatically after 50 boxes have been counted. When the counter's accumulated value reaches the preset, the done bit C5 to 0/DN turns on. That bit breaks the motor circuit, de-energizing the conveyor motor, and halts production until the next batch is started. If the operator presses the reset push button, the reset instruction C5/0 RES clears the accumulated count back to 0, allowing the process to begin again. The one-shot ensures the counter restarts cleanly without any false triggers or duplicate counts. This simulation beautifully demonstrates how the OSR provides precision and reliability in counting operations. Now let's take a look at the countdown counter instruction, or CDD. A down counter works the opposite of an up counter. Instead of adding 1 each time the rung turns on, it subtracts 1 from its accumulated value. In this example, the counter is C5:0 with a preset of 10. Each time the input makes a valid transition, the accumulated value decreases by 1. Below the counter, you'll see the important status bits. C5:0/CED is the enable bit. C5:0/DN is the done bit, which turns on when the counter reaches 0. And C5:0/UN is the underflow bit. This bit tells us the counter tried to go below 0, which usually means extra or unwanted pulses were received. The reset instruction works exactly like it does with an up counter. Resetting the counter loads the preset value back into the accumulated register. And as the note on the right shows, the setup for a down counter is the same as an up counter. The only real difference is the direction of counting. Down counters are commonly used when you need to track how many items remain in a batch or process. Now let's look at a practical example of combining an up counter and a down counter in the same program. This is a parking garage counter system, and it keeps track of how many cars are inside the garage at any moment. The first sensor is the enter switch. Every time a vehicle drives through the entrance and activates the sensor, the up counter C5:1 increments by 1. The preset value is set to 150, which represents the maximum number of parking spaces available. The second sensor is the exit switch. When a car leaves the garage, the down counter, also C5:1, decrements by 1. Because both instructions use the same counter address, the counter smoothly counts up for cars entering and down for cars leaving. As the accumulated value increases, the counter keeps track of how many spaces remain. When the garage reaches full capacity, meaning the accumulated value equals the preset value, the done bit, labeled C5:1/DN, turns on. This done bit drives the lot full indicator light and prevents additional cars from entering. A reset push button is included at the bottom. Pressing this button sends a reset instruction to C5:1, clearing the accumulated value and restarting the entire counting system, useful at the beginning of a new day or maintenance cycle. This is a great example of how PLCs can use both an up and down counter together to track real-world inventory. In this case, the number of cars inside a parking structure.